Okay. Yeah, sorry about that. So yeah, so this is a part of my research work, PhD research work. So we have actually studied the kind of groundwater, basically terrestrial water storage, which is measured by GRACE satellite data, which is primarily groundwater for the region which we have considered, which will come to that. So in India, and then we have studied further on the effect of urbanization and population density on the same. So yeah, so as you know that, I mean, groundwater, if not, I mean, the most important natural resources for the survival of human civilization, not only human civilization, maybe the entire life. But if you study this, so from kind of 1900 to 2008, the kind of there is a kind of considerable depletion of, I mean, global groundwater, which is around 4,500 kilometer cube, or is equivalent to 12.6 millimeter of sea level rise. Among these, the from 2000 to 2008, the average rate of depletion of global groundwater is around 145 kilometer cube per year. India being the largest user of the groundwater, India has a kind of overall kind usage around 230 kilometer cube per year, which is around more than 25% of global kind of consumption. And during August 2002 to October 2008, the mean rate of groundwater depletion has been like 4 plus minus 1 centimeter per year. Equivalent height of water can be, in other words, the volume wise, it will be like 17.7 plus minus 4.5 kilometer cube per year. And the total groundwater depletion has been like 109 kilometer cube, particularly for Rajasthan, Punjab, and Haryana and Delhi. This has been a study which is conducted by Rodell et al., published in Nature 2008. Uh, Now, major parts of India has actually kind of experienced like substantial decline of groundwater level, which is varying from 4 meter to 16 meters during 1980 to 2010, 30 years period. In 2017, the kind of the 60.53% of the global well observation, groundwater well observation wells have observed kind of uh, depletion compared to their mean period, which is, I mean, decadal mean period, which is from 2007 to 2016. Apart from the irrigation, urbanization, and climate changes have been like major factors which could affect groundwater storage. Among the various meteorological covariates, temperature and precipitation has been used widely to understand the depletion in the groundwater. In this recent study, which is published, which has been, I mean, I think in the Nature by Flemingeti, Rodell, and all, which has been like showing that um, there has been a high level of groundwater which has been in the north and eastern part of India, which also we have found, which will come to that, and the kind population trends and urbanization also has to kind of increased in this particular area. So we have thought of to study urbanization in depth to understand kind of, because urbanization primarily kind of drive population density. So yeah, so we kind of explored that particular covariates in our study. Now, as there is a small problem with the groundwater level measurement, because groundwater level measurement is by design is a kind of a discrete measurement. So it's measured by the kind of a depth to water below meter groundwater level, MVGL, which is basically with the help of observation wells. So it's basically a discrete measurements in space. We don't get a continuous measurement. So in order to get a continuous measurement in the space, so there are, many researchers has been used this GRACE data. We also have used, which is gravity recovery and climate experiment data, which is basically a twin satellite data. I'll come to that again. So that derived this terrestrial water storage data that helps to kind of give an estimate because that's have a strong positive correlation with groundwater level. So that has been used as a proxy measurement for groundwater level. So just to give a brief background on GRACE. So GRACE is basically a twin satellite. So this is just a image which provided by NASA. It's a joint mission by NASA, JPL, and DLR, Germany. So it's like twin satellites which are like 220-kilometer apart and around 500-kilometer altitude. So there is a K microwave measurement which measures the distance between these two twin satellites. And now this this distance is get affected due to the changes in the gravitational field. Now that is primarily caused by the changes in the terrestrial water storage. Now from that, um, so basically this the inter-satellite distance has been measured, and from that we derive the terrestrial water storage, which is a combination of groundwater storage plus soil moisture plus canopy water storage, and then snow, ice, and water in biomass. Now, if this data is available from the Grace Taylor's repository, and then this monthly TWS estimate for 1 degree resolution grid has been available. So this is we in this entire work we have mentioned is delta TWS, because it's all the data are relative to the mean baseline from 2004 to 2009. So that's why it's basically we have denoted it as delta TWS. Since April 2002, this data is available. Now, so now GRACE data has been used first initially by Rodel. Shown is in the GRACE data, which is monitoring the variation in the groundwater storage. Then many works has been done later also. Doyle et al. Have shown that the trend in the groundwater depletion with the help of again TWS and data. They have found that GWT, basically groundwater depletion rate, in the first decades of the 21st century has highest level of GWT occurred in India, US, Iran, Saudi Arabia, and China. Also, the GWT, they also found that it might be more than double since like 1960 to 2000. So that now the depletion rate has been the rate has been double than what it was from 1960 to 2000 period. Chinoshami and et al. They have again used this, and then they have also combined GLDAS, which gives us soil moisture estimates uh, to understand the again groundwater depletion trend in Tamil Nadu states in India. So these are some of the other works. So in Samsudha et al., they have showed in the study that GRACE dataset for GWT has a strong correlation in situ with the borewell measurements. We have done our work, which has got published in Journal of Hydrology. So there we have shown that GWS fluctuations. Basically, we can predict GWL fluctuation with the help of GRACE TWS measurement. We've done it on the 5 different geographic, and we got a very strong rho, which varies from around 0.604 to 0.8619. If we throw other meteorological variables also, it grows high, but only GRACE also is a very strong indicator for the particularly those places where the impact of other components like the ice and water, other water storage is negligible. uh, uh, just to kind of this canopy and soil moisture, we have found that they have a very positive strong relation, and their effect is negligible, which was previously also reported. So that effect is negligible, but yes, ice and those effect would be important, but the regions which we considered, it's not that important. So we found that this is a very strong indicator for the groundwater storage. Yeah. So with that, what we have done is, so for that 1 degree resolution grid, what we have done is we have done for entire like 286 grids of India, which covers entire India. That we have done we have studied it across the time, particularly from January 2003 to January 2007. Now, the month is very important because the water level grid fluctuated based on, because it has a seasonal variations. So in order to kind of take care of that, we have taken only the month. Now, the data what we're seeing it here is basically so delta TWS data for January 2007 minus delta TWS for January 2003 for the 286 grids. So it can be observed that in the entire kind of this Gangetic Brahmaputra basin, that it has been completely gone red. So we have observed like around 186 of basically 65.04% of the grids have in India. We can actually, these hilly regions and all we can neglect, but at least in this region, the northern and the eastern part, we can see that very considerable amount of this thing, which is greater than 20 centimeter, observed for around 555 grids, which basically uh, consists the states which are like Uttarakhand, Uttar Pradesh, Jharkhand, Bihar, West Bengal, Arunachal Pradesh, Assam, Meghalaya, and Nagaland, and Northwest India also, which covers states like Rajasthan, Punjab, and Haryana. Now if we cover, so this is between this. Now if we observe, this is slightly different data. If we observe, uh, now this is on the decadal so basically January 2007 minus decadal mean for the January data, which is from 2007 to 2016. So if we consider that changes, then we see like 281 grid points, which is basically 98.25, they have a considerable kind of negative changes in the delta TWS. Again, similarly, that greater than 10 centimeters and all that again observed in the kind of the same region which we have kind of observed for these also. Yeah, this is just a kind of another representation, which is basically um, only on the kind of Ganga Brahmaputra river basin and the northwest states of India, which is kind of, this is the left one is the January 2003, and then you can see on the right one, which is January 2017. So you can see the considerable amount of, it has gone from blue to red. So considerable amount of kind of depletion has happened during, I mean, in this region. So we have done further analysis. So what we have found is, so we have studied this, and then we have compute in this in the trend, which is January 2003 to 2017. We compute for each grid, we compute the trend, and we also compute the p-value associated with the linear component of the trend. So basically, we wanted to know that whether there is any significance of the trend, and we have found that in that entire kind of that particular zone which you're saying, though other places it might be there are some depletion or this thing, but there is no considerable amount of this thing. Only those places where it is like showing the color, there is a kind of significant trend and all. Apart from that, apart from some part in the north and some part in the south, that everything like the entire, again, the regions of our interest actually have experienced a significant negative linear trend during January 2003 to January 2017, and this is around kind of this varies from minus 2.2 centimeter per year to minus 0.01, with an average of minus 0.912 plus minus 0.455. So that's a kind of, that's a linear trend which we have kind of observed. Significant linear trend, because p-value is, so for these components where we are seeing it is basically the p-value is less than 0.05. In the same time, what we have also observed that the precipitation, we have taken these for the same time, we have considered the precipitation, we have considered the um, I mean, other meteorological variables like precipitation, maximum temperature, minimum temperature. So we did not find any trend for temperature, but we find trend for the precipitation. Now, extremely interestingly, is counterintuitively, the precipitation has a positive trend in this particular region. So this is the precipitation trend for this particular region, which clearly show that precipitation has increased. The right one is basically the temporal variation of the precipitation. We have taken a window of 8. So that also has kind of, so the variation also has increased. So we'll see that later. But in the left curve, which you see right now, there is a there is significant linear positive trend for precipitation. Now that means, and there is no trend for, we have not found any trend for temperature. That means that the meteorological variable temperature does not have any trend. Precipitation has increased, but still groundwater, or at least terrestrial water storage, which is indicating the groundwater, that has come down. That means that there it's not a meteorological variables which is impacting. It is primarily the anthropogenic activities which is impacting this. So we investigated further. What we have found is this particular belt of India, this particular belt is extremely fertile because it's like Gangetic plain and the Brahmaputra plain, and this is kind of compared to the rest of India, which is like 50.58% of like cultivable land, and cultivated land is 43.5%. This region has cultivable land is 63.64% compared to 50.58% of the rest of India. Also, it also has experienced kind of groundwater. We have also measured the I mean electricity consumption in agriculture sector, which is electricity consumption is primarily indicate the kind of groundwater pumping. Now, if that indicates the groundwater pumping, so that means that and we can observe that that growth has been significantly higher than the rest of India, which is like 80.6% growth, uh, which is basically with a CAGR of 7.67. With the rest of India, it's 72.3 and CAGR is 7.04. So the groundwater pumping has been higher in this particular region, which might be because of these fluctuations also. So it's like the more temporal variation in the precipitation which we can see also indicates that the dependencies on the groundwater might be more for the cultivation purpose. That might be one of the reasons, but because of these reasons, the groundwater pumping, the groundwater withdrawal has been more in this particular region. Now, then we also see the population density. So we have observed that this particular region, which has been historically populated, is not only has more higher population density from the rest of India, it also has a kind of higher growth. Like it has grown from like 307.31 to 382.54. From the rest of India, it was like 207.85 to 248.74. So it's quite higher than the population density of the rest of the India. Also, the increase is also high. It's like 24.97% it has increased, whether the rest of India, the population density increase of 19.67. We have found that this increase in the population density, for we have considered all these grids, and we have computed the correlation with the delta TWS grace derived, and we have found a strong negative correlation of rho minus 0.3128, which is significant. The p-value is again less than 0.05. So we have an kind of understanding that that anthropogenic activities which is being measured or being indicated by the population density as well as the uh, groundwater withdrawal has definitely impacted groundwater storage. So yeah, these are the sources of the data, and also GRACE data as population temperature I have taken from NOAA CPC PhD, population data land scan, population density estimate. So and state-wise data we got from the kind of India statistics book from Ministry of Agriculture and Farmer Welfare. Yeah, so these are the conclusions which I primarily concluded, that it's because I mean the precipitation has increased and also there is no much impact of the meteorological variables. It's the anthropogenic activities which is impacting the um, groundwater storage, which is being as kind of indicated by grace delta TWS. Now that when we investigate further, we found that groundwater withdrawal has been more for the agriculture purpose. Also, uh, the population density also has a negative impact on the grace TWS. Now we thought of kind of explore more and to study urbanization, because urbanization primarily drives population density. So we thought of uh, study more on urbanization and then see the impact of the same. So for that purpose, what we have done is, it cannot be visible slightly, not more. So it's like we have taken so we have not done only on that particular plane, because that would be kind of more simplistic, because anyway urbanization will have a positive inclination and groundwater has a negative inclination. So we thought of taking different 9 different places across India, where we got the prime criteria of to select those states were like it should not be a coastal region, because that it might affect other so grace delta TWS may not indicate groundwater storage significantly, because if it is coastal and all, then ocean water and all will come to the picture. We have not considered the hill, because again of the same reason, ice and all might impact the groundwater storage measurement, which is measured by the grace delta TWS. And also we needed, because we have measured the urbanization with the help of we have developed another algorithm, index based classification algorithm, uh, and that has some dependency on the satellite imagery, primarily Landsat 7 and Landsat 8 that we have used. So Landsat 7 we have used. So we needed the cloud-free images, and also that is one reason. And also we have also taken those particular areas where we have a considerable amount of urban growth. So yeah, so these are the particularly these statistics have been named. So these are all like 1 degree resolution grid, because grace data is also in the 1 degree resolution grid. So I have come like the same kind of, in order to have the balance in the measurements. So I have taken a 1 degree resolution grid, and these sites have been named on the kind of the biggest city that it encompassed, that particular 1 degree resolution grid. So I've taken 9 sites. Yeah, so this is fine. So we have here that there are two other points. So we have developed this power b1 built up index, so that we have developed this index based algorithm, supervised algorithm. This is why we have developed it, because we have found that SVM or neural net will take a lot of time to kind of tune and to basically fine tune and all, and you also require, particularly neural net requires a lot of training data to kind of predict properly to. So what we have done is we have developed an this algorithm. This work got published in IEEE Transactions of Geoscience and Remote Sensing, IEEE TGRS. So where we have done it here, actually we have come up with a method which take very less training data set, just 100 kind of training pixels. So each pixel is basically 30 meters across 30 meter. So that it takes, and then on that it basically computes particularly index, and then it does a thresholding. We also have proposed a thresholding method compared to the Ursu thresholding method. We have proposed a bootstrapping thresholding method. So I mean, in this one is we cannot discuss it because of the time and all. So this is extremely fast compared to SVM and NN, because it does not require I mean tuning. And then also the efficiency is comparable with SVM and ANN. So SVM also performs well, but it is comparable with SVM. It's like it's not, there is not much difference. So yeah, and definitely better than neural net, because for the less number of trainings, a neural net cannot do better. SVM has a mathematical foundation which basically makes it works better for a noisy dataset. We also have found that another similar index-based algorithm, because all the index-based algorithm, what happened that river sands and all, if you have river sand, so that get misclassified because they have a very similar spectral profile of the urban kind of built up regions with the impoverished area. So because of that, it get misclassified. So to order to differentiate that, we have developed another method, which is BRSSI. Currently, this is under review. This work, it's on the Earth Archive actually. This is built up and reverse and separation index. So this work, or basically, if we apply that in conjunction with PB1 BUI, so then we can get extract the kind of urban pixels properly. So basically, so if the PB1 is between some, I mean, minimum value and maximum value, and BRSSY is between minimum and maximum value, then that particular pixel is a urban pixel or built up pixel, otherwise not. In that way, we have computed urbanization. There is two other points. One is like, because of the, we wanted to get a kind of average value. So we have, and we also wanted to take care of the SLC failure error. So we have compared for not a, for a particular year, let's 2007, if I compute this one. So I have taken medium value of all the pixels of that particular image for, let's say, for 2006 Jan to 2017 December. So like that we have computed. So temperature and precipitation, as I told, it's like same for the CPC kind of NOAA Ph.D. data, and population density, as earlier we have taken from global landscape population data set. Okay. Now this is the basically panel data set. So yeah, so you can see like 2003, 2007, 12, and 17. These are the 4 time period that you have considered. Then you have compute the percentage of urbanization, which is basically the number of built up pixel by total number of pixels, kind of into 100. Then population density as given by the landscape. Sorry, for the particular year. Then average maximum temperature, average minimum temperature. So average maximum temperature in the particular year. So if I'm saying from 2003 to 7, so that means 2003 Jan to 2007 Jan. So both January we have included, and then delta TW. Delta TW is again we have considered only on the Jan, because then only we can compare. Otherwise we cannot compare. This is just a kind of these are the output of those actually the urban. These are the our method, which is basically this is Delhi. So this is computed with the help of this is the urban classified or extracted urban area of Delhi, computed using our algorithm. So applying PB1 and BRSSI. Yeah, so that's that. So these are all these things. This is the top one is basically Hyderabad. So this is Bangalore below. This is Bangalore up. Yeah. Now what we have done is we have done that panel data regression model. So what we have found is, so initially what we have done is we have thrown like initially we have given like each variables one by one, and we have found that percentage of urbanization is significant. And then population density is not that true. So if we throw one by one, we have found the percentage of urbanization. We can see that average max, average minimum temperature is not significant from the p value. You can see only average precipitation and percentage of urbanization is significant. Interestingly, the interaction effect of percentage in urbanization and population density is significant, and it has a negative slope. Like percentage of urbanization also has a negative slope, and and average precipitation is a positive slope as expected. So the TWS has a positive slope with a precipitation, and also has a negative percentage of urbanization and population density. Now, if we throw both together, let's say average precipitation and average percentage, then we see like um, precipitation has a positive slope or urbanization has a negative slope, and like the R square value goes very high, 0.66. This one, if we throw average precipitation plus interaction effect, then R square value go further, 0.77 and all. Just to add this one, so there are kind of just to decide that whether we'll do a kind of fixed effect model or the random effect model. For each this model, we have run a Hussman test, and we have taken, if it is significant, then we have taken fixed effect model. Otherwise, if it is not significant of the Hussman test, then we have done a random effect model. But irrespective of actual random effect model, this is the data, I mean, which we can see here clearly. I've just summarized it. So if we just to summarize, so the percentage of urbanization and average precipitation, these are significant if we throw each of the variables independently. Now, among that, the percentage of urbanization has a negative slope. That means if the percentage of urbanization grows, then TWS, which basically indicates the groundwater storage, that comes down. If it is average precipitation, which basically has a positive slope, so that has a kind of has a direction is same. If we throw both together, then it goes it goes high. I mean, the entire, I mean, R square is explainability goes high. It's around 26.48%, urbanization and population density. If we throw like interaction effect of urbanization population density, if we throw average precipitation and percentage of urbanization, then the R square value goes higher, 66.93%. Quite, it's can explain. And if we take interaction effect of urbanization population density along with average precipitation, then it goes 77.76. Now, so the entire the summary is, so the interaction effect of urbanization and population density has a negative impact on the groundwater storage as indicated by the grace delta TWS. Also, uh, uh, precipitation has a positive effect on delta TWS. Now, just to kind of point out the limitation of our work, as mentioned, I was trying to mention this, the TWS is a measurement of changes in the groundwater corresponding to the regions, I mean, where there is the effect of the other components are minimal. Now, if the ice, water, or the oceanic component, those are like non-negligible, then this might not be the kind of the, I mean, so we need to consider that we cannot use directly grace delta TWS. But for those regions which are considered in this study, there is no, that noise is not there. Now, second is, as we have done this Landsat 7 data we have used to compute the urbanization. Landsat 7 is 30-meter resolution. That means each pixel is 30 meter. Now, it might happen, and it will happen, when the 30 meter, there would be urban and non-urban component like green or barren might come. So then our algorithm cannot be able to classify it properly, or it might get misclassified either ways. So that's another limitation. And then the performance of the developed and applied method, it might fluctuate based on, because it's on the reflectance value, and it's like passive data. That means that the solar reflectance value is primarily get captured. It's not a microwave these things, so it might vary. But to take care of that, we have not taken a single date value. We have taken a median value of like the previous year and the next year. So the entire that period, we have taken a median value, basically to take care of this issue. We can also observe that though BRSSI have applied in conjunction with PB1BI to reduce the misclassification between the river sand and the built up pixels, but there might be still some level of, I mean, misclassification we can observe across the river lines. Now that kind of, I mean, that's like one thing is, if it is that is steady across the period which you have observed, so then the effect of that would be kind of minimal on the parent data regression model. So yeah, but that is still some level of after this application also, the reduction also, some level of misclassification is still there. Okay, now future scope and this. So I mean, instead of Landsat, so there are new I mean, data is available, which is primarily Prisma, which is a I mean, Italian space agency's data, which is a hyperspectral data, which is around have 67 VNI band and 171 SWIR bands. So our hope is we'll be able to come up with another single kind of index-based classification algorithm instead of two PB1BI and BRSSI, which are doing it, which can classify in a far accurate and in a better way. So that's our plan. And then second plan is we have done in our in this work, we have done it across like kind of 9 particular space, I mean, regions in India. We want to do it across India for all the kind of 286 grid points, if not possible, at least 186 grid points, and like see entirely how does it, or do it across the globe. That's all. Done.
Thanks, Amritendu, for a very nice talk. If there are questions, it would be great if people can share the questions on the chat. So, in the meantime, I had a question. This how reliable is the satellite data? For instance, Grace, in measuring this
Groundwater.
the information that you get, right? And how do you account for? I am pretty sure that there would be some uncertainty in the measurements that they make because it's a distance that they are measuring, and there could be some errors there. So how do you? What is the impact of that error, and how do you incorporate that in your model?
I mean, so we have taken, so I mean, NASA provides a kind of, they consider these things, and then after that only they provide kind of this estimation of the terrestrial water storage, which is like from the GRACE measurement. So we have taken that particular data, and along with that, they also provide the kind of error which can go. Now, as I have said, that error can go considerably high if you have kind of other components, which is like ice and the ocean water and all those things. It is, we have done in our initial work, which was where we have shown that its correlation with grace and groundwater level. There we have found that soil moisture effect and all has been negligible. Earlier work with Rodel and all also have shown that this is soil moisture effect and all are negligible. Also, it is like highly positively correlated with TWS, which and so don't want to throw again both the kind of correlated covariance does not make much sense. It doesn't improve the model. But like if particularly the places for the hills and all, it will not, might not be suitable. So we have not considered that.
Okay. And what kind of band do they use? Is it KU band or
K micro? Yes, sir.
Okay.
K micro.
So, so that would require an antenna on the other side, right? Like I imagine like dish TV, but okay. Yeah, that's besides the point. If there are no other questions, and given that we are running a bit late, we can move on to our next speaker, that is